Hello, in this video I'm going to solve the following problem for you. Evaluate the following integral. Integral dx over x squared times x squared minus 1 to the power of 3 halves. That would be a good idea if you pause the video at this point and try to solve the problem yourself first. If you do the calculations correctly, one possible answer that you will get is as follows. Minus x over square root of x squared minus 1 minus the other way around, square root of x squared minus 1 over x plus a constant c. Okay, so now let us solve the problem. So the existence of x squared minus 1 to the power of 3 halves in my integrand indicates that trigonometric substitution is useful here, and because x squared comes first, minus 1 comes second, that would be a secant function substitution. So I will introduce my theta to be secant inverse of x. Then it means that secant of theta is x. But something a little bit more, okay? Because this also tells me that theta belongs to the range of secant inverse function. So the range of the secant inverse function, if I denote it by this, is actually the interval 0 to pi over 2 union with pi over 2 up to pi. Okay, as you will see why I'm making it a little bit more complicated as usual, but just be with me and be patient. You will see why these are important to consider. Of course, in this case, theta is secant inverse of x, but I also know something. I know that x squared minus 1 should be greater than or equal to 0, but because it is in the denominator, should be greater than 0, because this is nothing except the second root of x squared minus 1 to the power of 3, so it becomes meaningless if x squared minus 1 is negative. So this means that either x is minus 1, less than minus 1, or x is greater than 1. Considering this constraint, I should take off 0 and pi from the range, because theta becomes 0 if x is equal to 1, and theta becomes pi if x is equal to minus 1. Now that I know that x equals to minus 1 and x equals to 1 are not acceptable, so I would say that let me take them off. So the interval would be the open interval from 0 to pi over 2 union with the open interval from pi over 2 to pi. So I will take this one off. So this is the range of this theta. So let me write a range of theta. Okay. Okay, so let us keep them here. And one more thing. If x is less than minus 1, theta will be in the second quadrant. And if x is greater than 1, theta will be in the first quadrant. So these are good to remember so that you will see when it becomes useful. So I will continue as usual. So I need dx. So I take the derivative of x here. The derivative of secant function is secant theta tangent theta d theta. And I go back here. If I call this integral I, so integral I becomes equal to integral. Instead of dx, I put secant theta tangent theta d theta all over x squared is secant theta squared. And then here it becomes secant theta squared minus 1 to the power of 3 halves. But what is secant squared theta minus 1? So we have this identity, 1 plus tangent theta squared is equal to secant theta squared, secant is squared, and then I move this to the other side, so this means that tangent theta squared is equal to secant theta squared minus 1. So what you see within the pair of brackets is nothing except tangent theta squared, but I have 3/2 of that, which gives me absolute value of tangent theta squared. Sorry, absolute value of tangent theta cubed. Why is that? For example, let me try to convince you like this. If I have x to the power of 3 over 2, this means in principle x to the power of 1 over 2 to the power of 3. Yes? So, and then it means square root of x to the power of 3. Okay? Now, if I replace x with this expression, so what happens if I replace x with so if I replace my x with secant theta minus 1, so this becomes secant theta squared minus 1 to the power of 3/2. This becomes secant theta squared minus 1 to the power of 1/2 to the power of 3, and then it becomes square root of secant theta squared minus 1 to the power of 3, yes? But this one is 10 squared, so this becomes square root of 10 theta squared and then to power 3. But the square root of 10 theta squared is not 10 theta, it is absolute value of 10 theta, and it is essential to consider this because I realize that theta is in the first quadrant, in which case I don't need absolute value sign, but it might also be in the second quadrant, but in the second quadrant tangent is negative. So writing this is crucial if you want to consider all the things that I mentioned here. So what you do, you will continue. Of course, 1 secant and 1 secant are simplified. I will be left with tangent theta in the numerator. I put d theta here. 1 secant theta survives. And instead of this, I just write absolute value of 10 theta to the power of 3. I hope that you understand there is no reason for me to believe that theta is an acute angle, to believe that theta is an angle between 0 and pi over 2, because this might not be the case. So I have to keep this absolute value sign. Now, I want to take this absolute value sign off, but I have to put a plus and minus, but I need to have a good understanding what's going on. So what I will do, I will say that this integral becomes plus or minus integral of 10 theta over secant theta tangent theta cubed d theta. But I want you to understand when this positive sign should be considered and when the negative sign should be considered. Positive sign should be considered if tangent theta is positive and I can safely remove the absolute value sign. So let me write it here. When do I choose positive sign? I choose positive sign when my theta is in the first quadrant, equivalently if x is greater than 1. So this means that either both of them are equivalent in this case. So either you can say it in terms of theta or you can say it in terms of x. So remember, plus sign should be chosen under these conditions and the minus sign should be chosen in other scenario, meaning that theta is in the second quadrant or equivalently x is less than minus 1. So I will keep them here for the future reference. So I just continue with plus and minus, but I have in mind that plus sign is used under this condition and minus sign should be used under this condition. Okay, so let us continue. So it becomes plus or minus. One tangent and one tangent are simplified, so I will get d theta in the numerator divided by secant theta tangent theta squared. I want to write this in terms of sine and cosine. So this becomes integral d theta. Instead of secant, I write 1 over cosine theta. And instead of tangent squared, I would write sine theta squared over cosine theta squared. And now what happens? Cosine times cosine squared, cosine cubed goes to the numerator. So this becomes plus or minus integral of cosine theta cubed d theta divided by sine theta squared. Okay, so how can I calculate this integral? That's also a standard integral. So you need to remember to decompose this cubic term in cosine as cosine theta squared multiplied by another cosine theta d theta, and then you have sine theta squared. Okay, why this is useful? Because I want to use the method of substitution by introducing variable u to be sine theta. Why this is useful? Because then du becomes cosine theta d theta, and I also need cosine theta squared, which is 1 minus sine theta squared, and sine theta is u, so it is nothing except 1 minus u squared. So if you apply these substitutions in this new integral, keeping the plus minus sign, it becomes plus or minus integral. Instead of cosine theta squared, I just write 1 minus u squared, yes? And then instead of cosine theta d theta, I simply put du, and in the numerator, it is just u squared. Okay. So I just want you to understand that might be there are two answers that cannot be combined into one solution. Okay, we need to see that. But according to the problem, if you do it correctly, and if the answer in the problem is correct, we have to come up with only one single answer, but this is not exactly seen right now, because apparently we have two opposite answers. But let us see how it will go. So I will keep this plus minus. Then I want to decompose my integrand to 1 over u squared minus u squared over u squared. So it becomes two integrals. 1 over u squared du minus integral of du. And then this is extremely simple one. The primitive function is minus 1 over u, and the primitive function is just simply u, and I can introduce my constant here. Okay, I have to switch back to my old variables. First, I go from u to theta by replacing u with sine theta. That's extremely simple. So let me do it here. So this continues here, plus or minus 1 over sine theta minus sine theta, and then plus a constant c. Okay, now I have to switch back to my old variable, the original variable actually, x. So the information that I have available is this one. So using this information, I should be able to express sine in terms of x. I have secant in terms of x. I should be able to write sine in terms of x. So how can I do that? Okay, so sine theta squared, so let me write it with different color here. Sine theta squared is nothing except 1 minus cosine theta squared, but cosine is 1 over secant, yes? So it becomes 1 over secant theta squared. Why I did that? Because I want to express sine in terms of secant so that I can use that rule. So that's substitution. So it becomes 1 minus 1 over x squared, and if I simplify that, sine theta squared, I take the common denominator. This is the case, but I need sine, so I take square roots. Yeah, so it becomes square root of sine theta squared is equal to square root of x squared minus 1 over x squared. But the left-hand side is not simply sine theta, it is absolute value of sine theta. The right-hand side, the numerator is always positive, of course, because this is positive, but the denominator, square root of x squared is not x, is absolute value of x. So this is what I get. But I don't need absolute value sine, I need only sine. Okay, so then I have to consider two cases. Case number one, so let me write it with black now. So case number one, I see that what options I have. Let us assume that because I have two options, either theta is in the first quadrant or in the second quadrant. So if theta is in the first quadrant, what happens? If theta is in the first quadrant, as you see, as I explained before, x is also greater than 1. So instead of absolute value of sine theta, I can simply write sine theta because in the first quadrant sine is positive. And I can also remove that absolute value sign because x is greater than 1, automatically positive. But another scenario is that what happens if theta is in the second quadrant? And if theta is in the second quadrant, as I explained before, x should be less than -1. But the interesting thing is that in the second quadrant, the still sign is positive. That is crucial. So still I can remove the absolute value sign from sine safely and write it sine theta. But if I want to remove the absolute value sign from the right-hand side, the price that I have to pay is to put a minus sign there. So minus x, and I put the minus sign here. Okay, so the question mark is this. I have two cases now. Case number one, so let me write question one, question mark, case number one. Case number one is that when I choose the positive sign here, I told you already, when the positive sign is chosen, if I am here, and that exactly means this, so my substitution should be this. Okay, 1 over sine flipped, minus sign is there, minus sign is there, so it becomes minus x over square root of x squared minus 1 minus the square root of x squared minus 1 over x plus c, but of course no one writes the positive sign there, so the answer is simply this. Okay, but what happens for the second scenario, case number two? Case number two means that I am in the second quadrant. So case number two is the one that I choose the negative sign. The negative sign occurs under these circumstances, and that is exactly these. In this case, sine theta should be negative of them. But of course, then I have to pick the negative sign. So I pick the negative sign, but I also have to pick this one for sine theta. I have a minus sign here, a minus sign here. When I replace them, it becomes x over square root of x squared minus 1. Again, for the same reason, this becomes plus x over square root of x squared minus 1, and then plus a constant c. But look, now I multiply the minus sign here, I will get the same answer back. So I was lucky, even though it was necessary to consider these scenarios. But coincidentally, because of the algebra involved, I come back to the same answer. So this is the reason that I want you to understand this process of playing around with the definition, domain of the function, the range of the function, which quadrants you are dealing with. Because sometimes naively, people do this. They say that, okay, when you write secant theta is x, it means cosine theta is 1 over x. And then they draw a right angle triangle. And then, for example, they call this theta and say that one possible triangle for which cosine theta is 1 over x is the one that the adjacent side is 1 unit and the hypotenuse is x. Using Pythagoras theorem, we can calculate this. And then, of course, if I want to calculate sine theta, it is the opposite side divided by the adjacent side. It is not totally wrong, but it is not complete, because when you draw a right angle triangle, you are implicitly assuming that your theta is an acute angle. You are assuming that this is happening. But this is not the only case that we have to consider, because it is possible that my x is less than -1, forcing theta to be in the second quadrant, and this analogy does not work for that case. So I want you to understand these differences so that you can decide for yourself which method is better. So this is a precise way of doing things. And in this case, in both cases, I end up with two negative signs, yes? Because when I choose the positive sign, according to this analysis, I have to pick up the minus signs in, and when I pick the minus sign out, then I have to pick up the positive ones in, so the effect will be the same. Okay. Okay, so I hope that this video was useful for you. Until the next video, be safe and goodbye. Thank you.